Hi everybody, welcome to our next lesson. What we're going to look at here in our demonstration is something that I'm sure many of you are familiar with. I would be surprised if any of you weren't. And it is what happens when I take a pen, in this case it's a leaded pencil, I'm going to call it a pen, and place it into this cup of water. And a hint is sort of like, you can look at what's happening to my shirt through the water right now. You see how it's kind of bending like that? So let's take it. I'm going to place it in here. Right? And now if we look at the pen, you can see that out here in the air, where it passes through the glass, the light passes through the glass, and then when it reaches that water line, it seems like there's almost a bend in the pen, right? There's like a kink there. So for some reason, when the pen passes through the water, it appears to bend. Now here's the thing. Right here at that bottommost part of the pen, that's not where the pen is right now. It can't be, because we see the pen pointing straight from here. The pen doesn't magically bend when it's in the water, but we see it as bent. Recall, our eyes only think that light, or our brain rather, only thinks that light travels in a straight line, which means the light is coming from this point. Our brain says, oh, there's a pen right there, but that can't be true. The pen must be up here a little bit. All right, so in this lesson, we're going to explore why it is that the light is in the wrong position, right? The light is not where it's supposed to be because the pen is in fact up here, not down here. Okay, so let's jump into the lesson. Oh, I forgot the aim. There's the aim. Why does the pen look like it is bent when I put it into the water? Right, we see something kind of like this. This is kind of a terrible diagram, but you see the general idea. All right, cool. Let's jump into it. All right, so now that we've seen the demonstration, let's address this aim of why does the pencil look bent when it's put into the water. And just a reminder that this diagram is not great, but I think it gets the general point across. So to talk about this, we're going to have to talk about this thing called refraction. Now, you explored this a little bit in the web quest last week, and what you should have seen is that refraction is what happens when an object changes mediums. And what we've seen is that when light changes mediums, I said an object, I meant light, from one medium to another, it actually bends a little bit. Now, I'm going to take like a little bit of a detour. It's not really a detour, but away from light to talk about why refraction actually happens. And so here, I have this sort of cart, right? And this cart is driving along this path. And on the path, it travels at a speed v, okay? And part of this game is you want to like get these boxes with these little question marks on it so that you end up getting some sort of an item, right? And then that item can be used in the game. I'm refraining from using the name of the game because I don't want YouTube to block my video, but I think you all know what I'm referring to here. So the cart travels here, and the goal is to get one of these boxes. You all know from playing this game that if your cart is somewhere over here, right here are your wheels, you're now off of the track. You're like on like the dirt or the grass or something. And so as a result, your cart is going to go slower. It's going to go at v prime. Okay. Now I see I've already made a big mistake. I made red the slower color, and everybody knows that red is faster than blue, but just follow along with me. So blue is faster than red here against all logic. When you go off of this actual track, your cart will slow down. Now, we've all probably had this experience where you swerve to try getting this box to get items, and you overshoot a little bit, right? And so as a result, your cart may look something like this. Okay, so you have two wheels that are on the track here, and you have two wheels that are off the track here. The direction of your car's motion is this way, right? You're kind of like going straight this way. But now, notice these two wheels that are off the track are going to travel at v prime. The two wheels that are still on the track are going to travel at v. So I now have the wheels on the track going faster than the wheels off the track. The consequence of that is that the cart will turn, right? It's going to turn because these wheels will move more distance than these wheels will. And that's kind of the definition of turning, isn't it? One half of the car moves more than the other half of the car. And so as a result, my path goes from this line to kind of like this line. Notice that bending of the cart's path is a consequence in the change in the speed of the cart from this medium, where it's v, to this medium, where it's v prime. So when this happens, what we can say is that the cart, ignore my spelling on that one, is in fact refracted. Ooh, what did I do here? Okay, the cart is refracted because when it changes medium, it changes speed. When we're talking about the refraction of light from one medium to another, we're going to talk about what's called the index of refraction. The reason why we're going to talk about it is because the index of refraction relates the speed of light in a vacuum to that in a medium. Because when light refracts, when we see this pen bending in the water, it is entirely a consequence of the speed of light in air, the medium that's around me right now, compared to the speed of light in the water and the glass. Okay? So since it's that ratio, I think we can easily come up with our equation. The index of refraction is going to be equal to the speed of light in a vacuum, lowercase c, over the speed of light in a medium, just like that. So it's a ratio. Let's recall that c is equal to approximately 3 times 10 to the 8 meters per second. That's a constant. That is the speed of light in a vacuum. And now here's a little thing we do. It's a bit tricky. Because air, of course it's not a vacuum, but it's a lot of empty space, right? We just sort of have these like gas molecules bouncing around, but other than those, it's empty space. We say that light travels the same speed in air. Now, of course, it's not true, but it is a close enough approximation to be true, all right? Because of that, air and light and a vacuum have the same index of refraction. So the index of refraction of air, we will say, is going to be equal to c over c, or 1. Right? That's the index of refraction of air. A few important things about the index of refraction. One is, if we take a look at this, we have meters per second over meters per second. Those are my units. And so I can say that this is a unitless quantity, and that should not be surprising since it's just a ratio, and ratios will be unitless. The next thing is that n will always be greater than or equal to 1. It can never be less than 1, because for it to be less than 1, v would have to be greater than c, right? But v can never be greater than c. So I'll put because v cannot be greater than c. All right, sorry, I know these notes are pretty terrible at this point. Hopefully it's clear enough to follow along. Maybe if I just sort of like box these things, it'll be a little bit clearer. Okay? And then we have this down here. So key, ratio of c to v. C is constant, 3 times 10 to the 8, and it cannot be greater. Oh no, I'm sorry, I put greater than or equal to. My bad. This should be less than or equal to 1. Right. I hope you've caught me up to this point. Okay, less than or equal to 1. Because v will always be less than c. All right, now, what does this mean? Well, suppose that I am going to move between 2 mediums. Here's N1 and here's N2. and I have light that's traveling in like this at some angle theta, and I'm going to call it theta 1 now. I'm not going to say theta I. It is the incident light, but I'll just call it theta 1. The notation makes it a little bit easier here. And let's say that when the light comes into the medium, I observe that it bends like this, okay, to some quantity here, which is what I'll call theta 2. We call this bending towards the normal. Okay, so the light has bent towards the normal. The angle has become smaller, meaning it's moving closer to it. Well, just like with reflection, we're only going to talk about the normal line here. We're not going to measure with respect to the surface, so just keep that in mind. Well, looking at this, what can we determine about the two mediums? Well, when it reaches N2, it moves towards that normal line. Let's go back to our Mario Kart example. If this is the direction of the cart, this first green line, and this is the bending of it when it refracts, and I'm moving from this medium to this medium, this is kind of like N1, right? And this is like N2. And this is like V1, and this is really, I put V prime, but we can call it V2. Well, isn't this bending towards the normal? So when the incident cart reaches the new slower medium, it bends towards the normal line, because here's my normal line, right? Isn't my angle getting smaller from here to here? Well, that's the same situation as here. So I can say that the speed of light in 1 is greater than the speed of light in 2, just like the cart is faster in this medium than in this medium. I also know that n is equal to c over v. Well, if that's the case, I can say that n1 is less than n2, because a greater n, let me use colored markers here, a greater n corresponds to a smaller v, because c is constant, and v is in the denominator. Okay, so smaller v, greater n. So I can say that light moves faster in 1 than 2, and the index of refraction of 1 is greater than the index of refraction of 2. I can also have a situation like this, where I have my medium here. It's a little crooked. I have light coming in like this, my normal line like this, and then the opposite happening. My light bends like that. Here I have theta 1, here I have theta 2, I have my index of refraction 1 and my index of refraction of 2. Well, imagine the go-kart coming in like this, right? Well, this wheel, the one that's represented by my thumb, is going to go faster, so it's going to turn this way. It's bending away from the normal, unlike in the previous example, and so I can say that V2 is greater than V1, and therefore n being equal to c over v, n2 is less than n1. All right, that's refraction. We haven't gotten to the math yet, but we can see when it bends away from the normal, it's speeding up, the light is speeding up. When it bends towards the normal, it's slowing down. Now, the law that describes the relationship between the indices of refraction, n1 and n2, and the angle of incidence and reflection, theta 1 and theta 2 I'm calling them, is called Snell's Law. And what it is, if I have a boundary here, if I have some incident light that comes in like this and refracts off like that, and this is my normal line, and I measure theta 1, and I measure theta 2, and I know N1, and I know N2. I know the materials, I know the indices of refraction. That index of refraction, I should mention, is just a property of the material itself. So like glass will have a different index of refraction of water than air, than plastic, or anything else. Snell's law is N1 times sine theta 1. Now you should remember from last week's assignment, the measurement of these angles was not a nice relationship. It wasn't something nice and linear. That's because of this. That's because it depends upon the trig function sine theta 1. And this is just going to be equal to N2 times sine theta 2. And that is Snell's law. All right? Just an equation that relates to 2, and we see that it depends upon the trig function sine. With that, let's look at an example here. So I have index of refraction 1 equal to 1. So it's air or a vacuum. And I have 2 equal to 1.5. And I know the initial angle. Well, I know Snell's law. N1 sine theta 1 equals N2 sine theta 2. This is going to be 1. I don't have to worry about units, which is nice. Sine of 30 degrees equals 1.5 times sine. Well, I don't know theta 2, so why don't we go ahead and solve for that? So 1 sine 30 is 0.5, right? So I have 0.5 over 1.5 equals sine of theta 2. I forgot to do this, so let me quickly calculate what that is. Okay, so when I plug this into the calculator, I find that theta 2 here equals inverse sine of 0.5 over 1.5, which is 19.48. If you look back at the example that you did last week, with that online simulation, this was one of the data points that I asked you to take, and what you should have ended up measuring was 19.5, right? So now we just have a little bit of a rounding difference, but it is consistent with what your measurements from last week were. We can look at another problem, or excuse me, it's going to be the same exact situation as last time, but we're going to graphically determine our index of refraction. So what does that mean? Well, let's say that we measured theta 1, okay, theta 2, and let's say we knew what the N1 was. Okay, we knew the index of refraction of the incident medium, something like this. Okay, again, we know that, and we know that. Well, if we're doing an experiment, what we're going to do is we're going to change theta 1 and measure theta 2. Okay, and we're going to do that to find N2. So we create a data table, right? And we put theta 1 here, we put theta 2 here. This is exactly what you did last week, right? But what are we actually going to graph? Well, taking a look at Snell's law, N1 sine theta 1 equals N2 sine theta 2. We're trying to solve for N2, so let's isolate for it. N2 is N1 sine theta 1 over sine theta 2. But we're not doing this for one data point. We're doing it graphically. So what we want to do is we want to label our axes. Well, what do we want to graph? Well, we want to, as we always do when we make a graph, we want to get this in the form of delta y over delta x. So what should our delta y be? N1 sine theta 1. We're talking about linearization here, right? What should delta x be? Sine theta 2. Well, now let's expand our data table. We want to have both of these here, so we'll put n1 sine theta 1 and sine theta 2. We'll plug our numbers in, get some data, make a line of best fit, solve for our slope of delta y over delta x, which is delta n1 sine theta 1 over sine theta 2, and that will be equal to n2. All right, and so what I'm going to do is I'm going to just quickly jump to a shot of my screen so you can see how I did this in Excel. Okay, so here, if you're looking at my screen, you can see I have that data that I promised. I've created some categories here. I have my angle of incidence, my angle of refraction, the sine of angle 2, and the n1 sine angle 1. I just plug these into Excel. You can see my equations up here for how I did it. I had to convert it to radians. Excel always uses radians. And, excuse me, from there, I created this graph. Here are my data points. I made a line of best fit and created the equation for the trend line. And here what we see is we have 1.4912 as my slope. You should recall, just like in the previous example, that the value of N2, the second index of refraction, was 1.5. So here we've experimentally come very close to the actual value. All right, so I hope that this example is clear, and feel free to look back at this or email me if you have questions about how I made this spreadsheet.